So a quick introduction to the Schrodinger's equations. So the Schrodinger's equation in general is minus h bar squared over 2m. Let's work only on one dimension. Psi over dx squared plus v psi is equal to I h bar d psi over dt. This is the time-dependent Schrodinger's equation. So what is the meaning of this equation? The first thing is psi is a wave function, because now we are treating the particle as a wave according to the de Broglie assumption, wave function. Okay. So here it is, as I have demonstrated in class, this is the kinetic energy. This is the potential energy, and this is the total energy. Okay, so it's just a way to write down the energy equal to the kinetic energy plus the potential energy, but by taking the particle or treating the particle as a wave. And in the case of a steady state system, this equation becomes, again, it only one dimension for the moment, plus v psi is equal to e psi. Okay, so this is the time-dependent Schrodinger's equation. Now, obviously, the steps that we use, the general step that we used for this equation is, the first thing is we need the input, and the input is the potential. We need a potential. And the second thing, once we have the potential, we try to solve for psi. So we get a solution of this equation as a wave function, psi. So the third thing, once we get psi, we start applying the boundary conditions. Boundary conditions means that different boundary conditions mean that the wave function must be finite everywhere. It must be continuous. Its first derivative must be continuous, and so on. So this we have seen in class. And once we, obviously, the normalization conditions, in the normalization conditions, the normalization condition also, because we need to make sure that the wave function is normalized. And the last part, once we have this, then of course we calculate the probability density function, because this one is the one that will give us the one that has a meaningful meaning, or meaningful physical meaning, and this will help us to calculate the expected values of the different observables. Okay, so let's give an example in this case. So here we have a small situation here. So an electron with energy E less than potential. So here we have an electron that is in close to well potential, and this electron has an energy, and this energy is smaller than the potential, and the electron is incident along the x-axis from left to right. So using the time-independent Schrodinger's equation, give an expression for the wave function for regions 1 and region 2, respectively. Of course, because here we have two regions. So the first thing we can do is write the Schrodinger's equation for region 1. So region 1. For region 1, so minus h bar squared over 2m. Of course, it's always, in this case, we have one dimension. There is no potential, so v psi is equal to 0, and it's e psi. This gives us we can easily see that d squared over dx squared plus 2m e over h bar squared psi is equal to 0. We can put this one as k1 squared is equal to m e over h bar squared, and then the wave function will have this general form is equal to a exponential I k1x plus b exponential minus a k1, this is k1 x. So this is the wave function in the first region. So region 2, so in region 2 we have again minus h bar squared over 2m d squared dx squared plus v psi. So in region 2 we have a potential, so we have to take into account this potential, and then we can easily rearrange the equation so that it will be 2m v minus e h bar squared psi equal to 0. Okay, v minus e, yeah. So here it's a minus sign. V minus e is a positive constant. So I can take k2 squared as 2m v minus e, which will be a real quantity. So d squared psi dx squared minus k2 squared psi is equal to 0. This gives me psi 2 x. Okay, here I should have done psi 2 everywhere. Psi 2, because it's the region 2, and here psi 2 has this form c exponential. Now the function is real. In this case, the function is real. Minus k2 x plus a d exponential k2 x. So this is equation for the wave function, the general solution for the wave function region 2. Okay. So this is question number 1. Question number 2, write the boundary conditions. Now, yeah, let me, so we have psi 1 x is equal to a exponential minus k1x plus b exponential minus k1x, right? I, so here I. So we have two wave functions. The first thing, we need to make sure that the wave function, when x goes to infinity, the wave function goes to 0. Problem with psi 2, which is a real function, when x goes to infinity, we can see that d exponential k2x goes to infinity. So this means we have to impose that d equals 0. So psi 2 becomes psi 2 of x becomes c exponential minus k2x, because d must be equal 0. Otherwise, the probability will be an infinite value, which is absurd. And then another thing is the function must be continuous at x equals 0, because at x equals 0, this is where the wave function changes from psi 1 to psi 2. The wave function must be 0, so psi 1 at 0 must be equal to psi2 at 0. And this gives me A plus B is equal to C. And psi prime 1 at 0 must be equal to psi prime 2 at 0. Again, psi prime 1, I can easily see that psi prime 1 is minus I A minus I K1A plus I K1B. Obviously, I replace by 0 also, x by 0. It gives me minus K2C. So those are the boundary conditions. Obviously, for this course, we don't ask you to calculate them, just to write it down. Okay. So the last question is write down the probability to find a particle in region 2. The last question is the probability to find the particle in region 2. Of course, again, let me just redraw this. This is, I have here psi2, and I have here psi1. Okay, obviously the probability to find the particle in region 2 is the integral from 0 to plus infinity, because I'm going from 0 to infinity, of psi2 dx, which is the integral from 0 plus infinity of psi star. Psi star is c star exponential minus k2x times c exponential minus k2x dx, and this gives you c squared, the integral from 0 plus infinity of exponential minus 2 k2x dx.